to my YouTube channel. Now this video, I'm going to present you another chapter from 5 Physics. Chapter 4, we talk about electronics. What I have here over the right hand side, it's actually the electron gun that you will see from your school laboratory. So you are supposed to go to the school so that you can have some hands-on on how to see how does it work, how this Maltese cross move, and make use of the left-hand Fleming law that we have gone through in previous chapter. So this we will talk about the science behind this electron gun, or we call it as it's actually called electron gun. Now to start off with, let's study this part over the right hand side. This is where the thermionic emission occur. So you should actually watch this video together with your reference and pause this video whenever necessarily and read on that particular section. So this part of the video is part 1 of it, or we'll talk part A perhaps. We'll talk about thermionic emission. What is thermionic emission? Thermionic. Okay, it means whenever your heat provided, the ion or the electron will be released from the hot surface over here. You see the red hot surface. So what is it? To make it a layman term, it's actually a process. It involves the emission of electrons from hot matter surface. So what you have here is the emission of electron from hot surface. Hot surface meaning the surface here, as the surface heated up here has to be hot. Sufficient energy for the electron to be released from the surface and then subject to high potential and then acceleration. Okay, so let's have a cross-sectional area view. If you want to sketch this into cross-sectional area view, so what is inside here? That would be a filament, hot filament, subject to potential difference. Here will be very low, perhaps only 6 volt direct current, DC. Okay, then what happened? This filament will be actually enclosed inside a chamber, a vacuum chamber. It's vacuum so that there's no air, so that you're able to see the electron when it's being accelerated and bombard on a fallen screen. You can't see electron, but the effect where the electron collide with the coating, then you are able to see it. Okay, so what is this here? It's actually a tungsten filament. A tungsten filament is a very high melting point metal, so you heat it up. So when current passes through it, internal resistance, heat is generated, and therefore electron would be free from the electron valence will actually be free and then ready to be accelerated. Then what happened next is subject the surface, this side, the next side, to really high potential, a lot of it. and then you have the anode side. So what happened? Because of this high potential, here easily we talk about perhaps 4 to 600, let's say about 400 V DC. Then what happened? This electron will be drift. Will be accelerated. So these are the electron emitted from the hot surface when you subject to high potential. High potential difference. Okay, now we will talk about what are the factors. There are a few factors affecting it. Okay, what are the factors affecting the emitted electron? Okay, first would be the surface area. Okay, you may refer to a reference text. What does it mean by that? Higher the surface or lower the surface, which one is better? Okay, then followed by, you may pause this video and then you read our surface area. Then second factor is called the temperature of metal. So if you do it in a very hot environment, therefore more electron has sufficient energy to be released from the surface, readily available. So therefore it can be accelerated easily. So the temperature of the metal. Then third, the type of metal. Type of metal. Whether you're using tungsten, you're using copper, yeah, it depends what type of metal. Some will be easier than another. One is easier than another. Okay. Then the fourth one depends on nature. Nature of the metal. Is it in oxide or not? Or pure? Or pure? Okay. Oh, the other page already. So if it were to be oxide, oxide or pure. If it were to be oxide, what happened? Oxide coated surface is very hard. It will be really, really hard to be ionized. So you need to provide very high potential difference in order to release an electron. So you don't want oxide layer, like aluminum oxide. It's very strong material against oxidation. So you don't want that oxide. You want it pure metal. So these are the factors affecting it. Essay question as usual. You expect those questions from the essay. Now, how are you going to explain what's the difference between thermionic emission versus evaporation? You have some books, yeah, look for a reference. They will talk about evaporation. Okay, evaporation occurs in any temperature. Vaporization, any temperature. Whereas thermionic emission occur at specific temperature. You need to heat up this surface of metal at certain level of certain temperature. Only then electron will start to be released from the surface, will be emitted from the surface. Okay, the prominent factor is evaporation, happens at any temperature, but not thermionic emission. So, how does an electron gun like this over here looks like? What are the component, perhaps you want to put it that way. So comprises of, this is actually the cathode, where it's connected to the Maltese. This is a cross, Maltese cross, cathode, and then here would have the anode. Okay, so you heat up the surface, you produce a beam of fast-moving electron called, they are going to have ray. They're going to have cathode ray. Okay, and this is what you call the cross. We call Maltese cross. I'm going to label this. It's actually a metallic cross, so that you're able to see the image at the Pendafloor screen. Okay, why you need Maltese cross is actually used to study the property. You were meant to study the property of cathode ray, RAY. So what happened? This fast-moving electron travel in a straight line. In vacuum. One thing I need to stress is actually a vacuum, meaning there's no air inside. Okay, fast-moving electron travel in straight line vacuum. It possesses momentum and kinetic energy. So you provide a black spot when they strike the fluorescent screen. So those that are being absorbed, or those that bombard on the Maltese cross, will be travel out from the circuit. Those that pass through it, okay, will bombard on the surface or the screen, and then you form a green image, where the dark image is actually the area where the electron bombard onto the screen. Okay, it's used to study the cathode ray, because if you were to apply magnet onto it, and you will see whether the image will move up or downwards, okay, based on left-hand Fleming rules. Okay, developed by magnetic field. That's how it works. Now, when this cathode ray strike a heavy metal, if this is a heavy metal, let's say palladium or copper, heavy meaning the number of proton inside this metal is high, then it's considered heavy metal. It's not because it's very high in kg. 10 kg is heavy. No, it's not the case. It's heavy means the proton number. Let's say copper, it's considered one of these heavy metal. If it were to be copper, pure copper, what happened? If you bombard it with cathode ray, what happened? You will see the surface, or perhaps it would emit X-ray. Yeah, it will emit X-ray. For the case of heavy metal. Okay, this is not heavy metal, so it will be safe. You do it on a glass and in your classroom. So what happened? From what we have learned from past, we have potential energy, V voltage. It's actually work done per unit charge. This is work done. This is unit charge. It means if you have two surfaces, positive, negative, and in the event you have a positive charge in the middle, of course the positive charge will be attracted over the negative, right? Now, if you were to bring this this test charge, positive charge, you call test charge, you want it bring from the negative side, you want to bring it, I want to bring it to the positive side over a distance, perhaps x. Okay, so therefore work is done. Work done per unit charge, Q positive, would therefore be actually the potential difference. Right? And in terms of unit, work done you need measure in joule, obviously. Okay. So what happened in the event for a cathode ray, a negative to a positive, so the work done or the transfer of energy from potential to kinetic, okay, the electrical, we're talking about electrical potential energy, because you might confuse with gravitational potential energy to mgh you have learned in Form 4 Chapter 2. So here we talk about electrical energy. So the electrical potential energy is in joule, okay, and it's joule, so therefore it's called E Hui. It's actually electron volt, unit as in joule. So the electric potential energy is actually converted to kinetic energy the moment when you accelerate it. You will convert it to kinetic energy. Where the equation would be half m mass of electron v squared, where this is the speed. Some question, they will ask you to look for the speed, give you the potential energy. ME, mass of electron, you'll be able to get it from your calculator. You look at the back of your calculator, the hard cover, the mass ME, you'll be able to get from the calculator, which is 911. Okay, if just in case you doesn't know how, you go to constant, you press 0.3, okay, and you should get this value reading. ME would be 9.11 times 10 power minus 31 kg. Okay, this is the number. You go to your calculator. You need to refer to the hard cover of your calculator. For mine is 0.3. You press on constant 0.3, and this is how you recall this number. Then for the charge of an electron, now charge of an electron, say this one here, charge of an electron, E constant 23, you will find that it's 1.602 is actually one of those constant you were able to find from constant book, or just in case you didn't give you Coulomb, C Coulomb, you're able to get it from the calculator. So constant 23, for your calculator, kindly see if you know how to call this number. I mean, you call this constant, and as well as with constant 3. Constant 0.3. Right? Recall these two number. So to put that into an equation, perhaps that would be, therefore, electron volt, it's actually half mv squared, because all of this, remember about the squared. You know, student tends to forget about the speed in terms of meter per second. Always forget about this. So in the question give you how many electron volt, and then they ask for speed, and this is how you should use. You should make use of this equation of relation to look for the speed of the electron. Alright, so just like any other video, you should actually stop this video and look for the chapter by chapter, from 5 chapter by chapter exercise, and at least try out at least 5 to 8 questions, so that you get the hang of it, how to actually get used to question relates to cathode ray. Now, I will not be able to show you how the movement should look like. Over here, I can't actually show how it moves, because it's really hard to show it here because it's a side view. Okay. Perhaps let me give you an example. Now, over the next page, perhaps. Easy. You get to see those questions. They ask you about where the direction of the cross would look like. Right. So what it tells you here is, perhaps I have actually a north and a south magnet, north-south magnet. Okay, cross-sectional view. And this is actually, if I were to look from here, so at the outside of the image from here, and then north is over this side and south is over this side. Okay, initially I would have a Maltese cross look like this. Okay, without the magnet. Okay, and obviously the direction of electron is coming out. So I give it a dot, perhaps. I give it a dot, meaning the electron coming out from the surface. Okay, coming out of the surface. Now, what happened if you were to remember somehow your family left hand? You have father, mother, children. Okay, so here magnetic field is to the right. Current is going out, coming out from you, meaning in terms of fingers should be pointing this way, and then this is where your finger out, because current is follows positive and negative. Electron move opposite direction. So if in the event electron moving out, so therefore the electron move out, so therefore the current move in, right? So therefore you need to twist your hand 180, 190, so therefore you would expect your thumb, next finger, and then you actually can't see 1, 2, 3. It's into it, right? This is how you should do, not this way. So you expect the Maltese cross would actually drift downwards if you apply a magnetic field based on this coloration. Current move from positive to negative. This is electron. Electron ray out, coming out of plane, coming out from you. That's why a hole is a dot. Okay, coming out from you. So therefore, current goes in. That's why current goes into the plane. So you expect the melted cross would shift downwards. Okay, you expect this kind of question. The direction of current move opposite where the electron gun moves. Okay, so that's all from me. If you're the first time watching my video, kindly subscribe to my channel. Stay tuned to my next following video. Thank you.